Gian ready na.
Good day, everyone. Welcome to Super November AstroCHATS. We shall start our program with a short toxology performed by the RTU Himig Rizalya, to be followed by the singing of the Philippine National Anthem.
Mga kababayan, ang pambansang awit ng Pilipinas.
Tayang mag-ibig, pero sa silakanan, alam ng puso, sa titik mo'y buhay. Upang hinirang, kuya ka ng magiting, sa mandulubing, di ka pasisigil, sa nagagatutok sa simoy at sa langit mong pamraw, ay hinatang tulad, awit sa pagkayang minamahal, ang isang ng patawad mo'y buhay na
Magandang umaga. Sawadee Kap, Thailand. Good morning. I am Gian and I will be your MC for today. Thank you for being with us today and staying with us despite the scheduled program due to the previous bad weather. Moving on, allow me to describe our program AstroChat. AstroChats presents delicate multidisciplinary short talks from different professionals. It aims to provide free knowledge and ideas to the Filipino people on the diverse relation of astronomy in the fields of arts, science, and technology. We have two resource persons for today. This year, Super November AstroChats is indeed a luminous program brought to you by the Department of Science and Technology, Center for Astronomy Research and Development, in close cooperation with the National Astronomical Research Institute of Thailand, the Department of Physics, Mapua University, and sponsored by the International Astronomical Union Office of Astronomy for Development. To formally start our program and to introduce our resource person for today, let's welcome the Program Officer of the Center for Astronomy Research and Development and the Director of Research and Development Center, Professor Ryan Manuel D. Guido.
Hi, good day. So, welcome to Super November Astro Chats. So, our Super November Astro Chats for today, we'll be having a whole day event as our last Astro Chat episode for this year. Okay, so please stay tuned for us by next year. So, our distinguished resource person is from the National Astronomical Research Institute of Thailand. So, it has been 5 years since 2015, since RTU and the Department of Earth and Space Sciences, the Center for Astronomy Research and Development, and the National Astronomical Research Institute of Thailand forged into a collaborative efforts for astronomical training and researches. So we have started the Astronomy and Astrophysics Data Research Analytics Workshop, or ANA DRAW, which was held last August 2018. So the series of international workshops being hosted by NARIT to our faculty and students through their training programs. So in which our resource person for today is one of our trainers during our training at NARIT. So also, this event is being co-sponsored by the International Astronomical Union Office of Astronomy for Development. We hope that you stay with us throughout this special whole day event brought to you by RTU and NARIT. So our resource person for today is a researcher at the National Astronomical Research Institute of Thailand. She is an active member of the International Astronomical Union Division G for stars and stellar physics. Our resource person specializes on extensive research on closed binary systems, mass transfer and common envelope processes, and stellar evolution, single and binary star. Ladies and gentlemen, we are pleased to welcome live from Thailand, Dr. Puji Irawati.
Thank you very much. Good morning. My name is Puji Rawati, or many people call me Ira. So I'm very honored, and I would like to extend my gratitude to RTU to invite me today to give a little bit of talk on stellar evolution. And here in Thailand, we, as mentioned before, we have a long standing partnership with RTU in the Philippines, and it has been a great collaboration since we first started a few years back. At NARIT, we've been, as you know, as a neighboring country here in Southeast Asia, we share many similarities in terms of people, culture, economic development and situation. So we are not that different. And at NARIT, we are still trying to improve ourselves, and I hope that we can do it together through our collaboration here between NARIT and RTU, and hopefully also with the other universities in Thailand and in the Philippines. I remember a few weeks ago at the beginning of the month, we've been listening to the talk by Dr. Utan, and he's been giving some message about the astronomy at present day, and we are now at the challenging situation. And I would also like to extend my condolences, and I'm really sorry for what happened in the Philippines in the past a few weeks. It's been a trying situation, and it's a hard time for everybody there. But I hope everything will get better for you very soon for a beautiful Christmas and New Year later. Despite that, I would also like to mention that this year has been a challenging year for me and for many people at Narit in Thailand and also in the world. The current situation, from what I see from my personal point of view, it is a very difficult and it is very challenging. But apparently, in the astronomy world, from what I experienced in the almost in the past year, since the beginning of this year, is that our work in astronomy seems to go on as expected, and I would say it's even better. So the fact that we've been confined to limited resources, that we cannot travel, we cannot meet our colleagues in person, talk to them in person, is is a challenge that improves the way we work in astronomy. And I have to say that when I talk to some of my colleagues, they even say, actually, the current working situation is, for some of them, is actually better, because in astronomy, we work at odd hours, weird hours. Some of us work in the night, some of us work in the day, some of us work on any kind of time of the day, because we have to follow some astronomical events that happens on a certain time. And so for us, working at weird hours is normal. And the fact that we can work online, actually, it's improved. It forced us astronomers to really exploit all these online meetings, emails, online collaboration, and it worked. For astronomer, it worked. Our conferences work as normal. We've been having a lot of online conferences, and it seems to work. Some of us has to join from different part of the world. So some of us connecting at 2 a.m. in the morning, some of them connecting at noon or in the evening. It's really weird, but from what I have to say and what I have experienced in the past few months, it made our work in astronomy. We've seen a different view of working in astronomy in a totally different way. And from what I see, it didn't stop us at all. The work, the collaboration, the teachings, the supervising the students, the data analysis, the collaboration, it's still going on, and even stronger, because we can reach our colleagues easier now. All right, so despite that, in astronomy nowadays, and I will mention a little bit also later, astronomy is a unique field where development happens really fast. All the topics, the new topics, changing and coming at a really, really unexpected speed. Years back, when I was still a student at the university, the big thing was exoplanet, finding new exoplanets. Now we have tons, thousands of new exoplanets. And then few more is going on. And nowadays, maybe you have heard about gravitational waves, fast radio bursts, and finding the optical counterpart. So I find myself here working in astronomy at present day. it's still very challenging for me. I have to keep up. I was, as mentioned, I was working initially in binary star, closed binary compact system, but now I have to keep up with the present topics, meaning I'm working on fast radio bursts, I'm working on asteroid, I'm working on many other things because that is what astronomy demand the people in the field to do. We cannot stay still. We have to change, we have to improve ourselves, we have to keep up with the latest development. So my message for all the young people out there, um, astronomy is a very exciting field. And if you are really considering to work in astronomy, you have to prepare yourself to keep studying for the rest of your career. So even now, this is me 20 years later, not a student anymore. I'm still studying new topics, new papers, new methods to make myself still able to keep up with the present day changes in astronomy. And I really cannot tell you what will you experience 5 years from now, 10 years from now. And I also possibly have to prepare myself for that time when it comes. But that is astronomy. It's very demanding. We often, well, actually, I have to say, before the pandemic began, many astronomers has to travel all over the world to reach our telescope, which is located in the most isolated location on Earth. The pandemic changed all that. Some of us are struggling to get the data. Some of us are still managing because some of the observatory are very kindly doing service observation for us. So they are still taking data without us having to travel to reach the telescope. So our work still progressing. And in the future, you've seen lots of space telescopes being sent up, a lot of new facilities being built. It's our telescope is getting bigger and bigger and more massive. Nowadays, that just what happened from when I started astronomy 20 years ago. So in the next decade, I really cannot guess, cannot say what will happen, but for sure it will be an exciting and I would say unexpected experience. So for those of you who would like to work in astronomy, prepare yourself for this kind of challenges and that you have to keep yourself up to date with the present situation and keep yourself up to date with the new method, keep studying. And in Southeast Asia, I come from Indonesia. So again, very similar kind of situation where astronomy is always being questioned. What will you do in the future? I was one of the lucky ones that my parents supported me when I told them I want to study astronomy at university. Still, 20 years later, I get the same question. When you study astronomy, what will you do later? I want to say that I will also give you later a brief message that astronomy is a benefit. And you will see later through my talks that through astronomy, I gained so much. And actually, some of my friends, some of the colleagues that I know, they can apply their knowledge, not limited in astronomy only, but in other fields. So astronomy is a very robust field which can be applied to many kind of disciplines, um, including medicine. Some of the astronomers, they are working. Some of the astronomers are working with medical doctors to analyze this big data, which already mentioned by Dr. Uten in his talk. So astronomer is a person which is capable of doing so many things, not only astronomy, but also working in other fields. So this is a message to students in the Philippines, Thailand, Indonesia, in Southeast Asia. I would say that through astronomy, you can obtain and you can gain so many things, and actually you can work in any place, in any field you want. So I think I will stop here and we will hopefully to start my talk very soon, and I will mention what later at the end of my talk what an astronomer can do during this pandemic, at this very challenging situation for all of us. Thank you very much.
Thank you, Dr. Puji Irawati. So now we can hear. Now we will see Dr. Puji Irawati's presentation for stellar evolution. Thank you.
Okay, I will start preparing my screen. Is the screen okay? And everyone can see the slide?
Yes, ma'am.
All right. Thank you very much. So good morning, everyone. I hope you can listen in well and clear from wherever you are. There will be a little bit of animation also later and the video. So don't worry if you cannot play it properly. All the links is there on the slide, so you can visit the video or the website or the image that you would like to see later. I will also provide the copy of my presentation slide to RTU, so you can also get the PowerPoint if you want from them. So my story for today's AstroChats is about stellar formation and evolution. We cannot avoid talking about stellar formation when we talk about stellar evolution. So on the screen, you see that it's an illustration, artist's impression of our sun evolution from what it is now at the lower left bottom of the screen to what it will be 5 billion years from now. So stellar evolution in a nutshell. So this topic usually at the university you will learn at least for one semester, but here I will try to deliver it to you within 1 hour. So it will be very compact and brief introduction on a stellar evolution. As you see on the screen, each star, depending on their size, will go through a different evolution in their lives. The small one will become a different kind of star, a white dwarf, or it's actually becoming a black dwarf. Some star like our sun will go through a red giant phase and the white dwarf later, and the blue massive star will end as a black hole or a neutron star. So you will listen how each of these stages happen in the stellar lives. So how do we actually study the life of stars when these stars, they are evolving on a time scales longer than all of human history? And so you will see how the astronomer get to this. And another question is, why astronomers have to study stellar evolution? Why do we have to know about stellar evolution? All right, so let me start. If you were in a forest and you would like to know how a tree grows, so how do we study the life cycle of a tree? They live for a big tree from a seedling into a grown tree. It will take decades. So, but you have only one day. So how do we do that? We observe, we see on ours, all of our surrounding, all the different kind of trees, different types, the heights, the size, the leaves, the pattern. We collect all the data possible. We make a model or theory, and then we try to apply it on our data. So this is what the astronomers are doing with the data of the stars to understand the stellar evolution. Our problem is we cannot visit our lab. The stars are located so far away. What we get from them are the lights which come from the outer part, the atmosphere of the stars. So as you see, when we observe the sun, here what we see is only the disk or the outer part of the sun, while the inner part, where many things going on, we now know that there is a nuclear fusion going on in the sun. How do we do that? I will tell you later in the next few slides, which will come. So this is what the astronomers have to do. We try to collect as much as possible data we can, and most of them actually are coming from the outer part, not the inside of the sun. And then we make a model based on what we know, extending to also the interior part of the sun. And we try to compare this model by taking and observing a lot meaning millions and billions of individual stars. All right, so this is one star, one sun, our sun, which is the closest to us. So now, what do we do here? So this is a zoom in to give you the idea of how many stars are there that we astronomers have to observe and have to study. So when you zoom in into the sky, a tiny patch of the sky will have so many different kind of stars. So each dot here is a star. And this is what we have, the astronomers, to study. So this tiny speck of light. So what do we have to do to understand how they were formed and how they evolved? So as you see here, there is so many dots. Some of them are bigger, some of them are smaller, some they are whitish, some are orange, some are blue. And if you keep zooming in, you will see more and more and more. So this is actually zooming in on one particular galaxy. So you can visit the video there later on the link provided. So this is just to give you an impression of the amount of stars that we have to study to understand stellar evolution. And it's not a trivial work, and it's a long process. All right, so what do we do with the data of all of the stars that we collect? We put them in a diagram. We call it the Hertzsprung-Russell diagram because it was first proposed by Einar Hertzsprung 100 years ago, and independently by Henry Norris Russell. So at the beginning of the previous century. So when we collect all of this, the data of all of these stars, apparently when we put them in a certain properties, as you see here, we have the temperature here on the bottom, and on the ordinate here on the y-axis, we have the absolute magnitude of each stars. When we put them in the same diagram, apparently they make a certain pattern. So most stars, they will be on this patch, what we call as the main sequence. As you see the size, so the size represent, it is not to scale, but it represent their sizes also, the real sizes. So when most of the stars are located on this main sequence, so you know our sun is located here. This is our sun, which is a G-type stars, with the outer part having a temperature of about 6,000 Kelvin. And if we look outside the main belt here, the main sequence, we see that the stars getting also smaller and larger there. So we have here the red giant star. Some of them are really, really big. And when we go towards the left bottom corner, we see the one smallest type of stars, the white dwarfs here. And so this diagram, the Hertzsprung-Russell diagram, is a very important diagram for astronomers. If you ask any astronomers, they will know what a Hertzsprung-Russell diagram is. So apparently this diagram also tells you much more later. It's not only telling you the properties of the stars. If you know a location of a star on the Hertzsprung-Russell diagram, you know in general their temperature, their brightness, the magnitude here, their size, the radius, and their mass. And it actually also tells you their evolution. So we will go through this together later. All right, so this is the theoretical Hertzsprung-Russell diagram, which was proposed by Hertzsprung and Russell 100 years ago. So this information, this knowledge, we got it not too long ago, 100 years ago. And nowadays, the Hertzsprung-Russell that we see in the present day, you see here, this is what we have now from the data of a satellite called Gaia. Gaia was launched in 2013 to make a 3D map of our galaxy. So Gaia supposed to survey, take data, precision measurement of billions of stars. And yes, several years later, Gaia produced the data here. As you see, this diagram consists more than 1 billion stars. And you see that the Hertzsprung-Russell diagram, as we know it, has dramatically changed. We still see the main sequence there. We still see the general pattern of the Hertzsprung-Russell diagram here, the larger star, and also the white dwarf here. Just apparently when we look, when we collect more data, we get more data. So here has the same Hertzsprung-Russell diagram, but with just so many more stars in there. So this is, again, the kind of amount of data that the astronomers have to handle, so billions. And thanks to Gaia, we got a better insight on the stars in our galaxy. For example, here, if I can go back to the previous slide here, you see just very few white dwarfs seen on this part, but not according to Gaia. Gaia found much more. And actually, when we zoom in to the white dwarf on the Gaia Hertzsprung-Russell diagram, we see a distinctive pattern of supposedly a different type of white dwarf there. And there is a tiny line going to the left here, which apparently confirms and tells you the interior of a white dwarf. And it confirms that the white dwarf, they have a crystal core here, which we suspect, the theory predicts that, but only now we can confirm this theory. So for astronomy, usually this process takes quite some time, but thanks to a lot of observation and a good theory and model, we can prove all of this. All right, so let's move on now from the present day Hertzsprung-Russell diagram. So based on this, as I mentioned, we want to know what the star's properties are before we get to know how they evolve, how they form. So it's the same like when you want to know a person, you need to get to know them first. So we try to find their information here about the star. What is their mass, their brightness, their luminosity. So here you see that I will use some of these symbols later. So this M dot or L dot, this represent the sun, while S here is the star. So we want to know the mass of the star as compared to the mass of our sun, the luminosity or the brightness, the radius, the size, the effective temperature. So basically this is how hot the star is on the outer part, on the atmosphere. So the age and what's actually inside. So X, Y, Z here, X is the hydrogen abundance, the Y is the helium abundance, and Z or Z here is the heavy elements. So for our sun, this is the abundance. So most of it contains of hydrogen, a little bit more helium, and very little heavy elements. The evolution of a star really depend on their mass. So mass here plays a very important role in a star's life. You will learn through this talk how is it evolve, how is it formed, which depends on the mass, how it will evolve depending on its mass, and how will end up later depending on its mass. And the mass that form a certain star, it will depend on the mass on where they were born. So the birthplace of the star, the nebula, which is contains of a hydrogen gas, it's important on the making of the stars. So in general, when we study stellar evolution, we will learn that there are different stages of stellar evolution, which is the formation, when the star was formed. This is the pre-main sequence. So when before the star becomes a star as we see now. The main sequence, you've heard this term already in a few slides before. Post-main sequence, where the stars usually, some of them becoming larger in terms of radius. And the endpoint, how it will become later. So you will see this plot many times more in the next slides. So this is just a brief track of how our sun will evolve in the HR diagram. So you see, you can recognize that this is the HR diagram now with the temperature on the x-axis and the luminosity on the y-axis. So where the stars were born, they are actually formed in star-forming regions, or what we call the H2 regions, H for hydrogen there. So this nebula, the birthplace of stars, they are a massive hydrogen nebula. So it contains mostly hydrogens. The size, the mass of this nebula, usually it has to be a few hundreds solar mass up to 100,000 of solar mass because they have to make a good number of stars. The size, so how big is this nebula on the sky? Here, typically it can be between 1 to 200 parsec. So this is 1 parsec is a few light years. And the temperature of this nebula, as you see here, is not too hot, but it will be between 10 to 100 kelvins. And in our Milky Way galaxy, we have a few thousands of them. So this is an example, pictures of Sharpless 29, a stellar nursery, so where some stars were born. You see here that the nebula has so many different colors. Some are blue, some other parts are red, some are actually black. So each of these means something. So as you see, color means temperature in astronomy. So as you see, blues are here, blue regions here usually hotter, as well as these blue dots there, you see it's hotter, while the red part is less in temperature. So basically this is a hydrogen dust, if you want to call it. So you see some of these stars here, they were really just born. This is the location if you're interested, and the size here is the field of view, what we call it in astronomy, is between 62 by 50 arc minutes on the sky. So not every cloud can make a star or stars. So a cloud has to be just right to host future stars. So apparently nature is very specific. You cannot just make a star even if you have hydrogen. So it has to be just right. And the criteria of when a nebula can make a star is here. They call it the Jeans criteria. I will not go into detail on this, but if you're interested, you can go through. This is an example of a book on stellar structure and evolution of a single and binary star. So for those of you at the university, maybe you would like to look into that. So basically with this Jeans criteria, we know whether a nebula can form a star or not. All right, so let me continue. What kind of stars will be born in the nebula? In nature, apparently, stars tend to form in groups, at the minimum binary. So binary stars are very common. It's very rare to see a single star like our sun, actually. So our sun is a very, very peculiar star. So most of the stars, when they were born, or actually when you see them, they form in groups such as the M45 or Pleiades cluster. Here you see the picture. So you see on the Pleiades cluster, all of the stars are blue, meaning they are hot, and they are used. You will learn later that this blue star, they are very young stars, while the orange, reddish one, they are old in terms of age. So they were formed much, much longer before. So Pleiades Nebula is a young cluster, contains of young stars. So what kind of stars, what kind of type of stars will be formed in a certain nebula? There will be many or a lot of small stars. So this is the spectral type. If you remember from the Hertzsprung-Russell diagram, K, M, L, and T. So this is also represent their temperature. There will be a few more massive stars. So A, F, G type stars. So G is the type of our sun. So this is yellowish kind of stars. These are all red. This is yellowish, and going here is whitish. And so there will be very, very few big stars or O and B type stars. So these are blue kind of star as you see in the Pleiades cluster here. And these O and B type star, they are the most important members in the cluster, so in the nebula. Because when they are born, these O and B type stars, they have so much energy that it radiates. Let's look at these star which were born in the nebula. I take an example here, the Eagle Nebula, a very famous one. So this, you see here, oh, I'm sorry, let me go back. So here you see the Eagle Nebula here. So this is on a different wavelength, we will see different information of the nebula. So it is important for the astronomer to take the image of the stars or of the astronomical object in a different wavelength. So we get the complete information of the object that we are looking at. If we observe the Eagle Nebula in the far infrared wavelength, you will see this, while in the visible, so usually in the optical or amateur astronomers usually will get this kind of pictures. This is already multicolor here. You see this Eagle Nebula. So as you see, when we compare the far infrared and the visible one here, they look different. So they tell you different kind of information. And if we go to a shorter wavelength here, X-ray, so using a space telescope, we'll see the hottest members of the groups there. So these are what I mentioned, the blue OB type stars, which are massive stars, which we cannot see from the optical or the visible wavelength or the far infrared wavelength. So when we combine all this wavelength together, this is what we will see. So most of the nebula is located, consists of hydrogen, red hydrogen. So you see that it's low in temperature, but near the most massive members of the nebula, the stars in the nebula, it's blue here. All right, so if we zoom in on the Eagle Nebula here, on the visible, near infrared, and the mid infrared, again, we see different kind of image. The nebula consists of dust, and it's a cloud. So it's blocking our view. When we want to see what's behind or inside the nebula, we have to use the wavelength which is capable of doing that, which means we have to use the radar wavelength. So this is the visible wavelength. When we observe it using the optical, we see mostly of the dust there. This is the usual image that we see. When we use near infrared, so longer than the optical wavelength, now the dust start to disappear. Now we see the stars behind the clouds, these clouds of nebula. So here you see this star here, which appears red because it was blocked by the nebula. So the blue part of the wavelength from that star is blocked away, and we see only the red part because of the wavelength effect. When we see it on the near infrared, you see that it is much brighter. And we see now a star which was hidden behind the nebula there. And if we go further in the wavelength, go redder, we'll see more here. And if we go to the head of the Eagle Nebula here, you see there are lots of radiation coming. So this is the radiation coming from this part here, which is a bright, massive stars there, which radiates its energy to the surroundings. And it actually helping the nebula to make more stars. So this is the importance of the star formation. And how does a star actually form? What kind of process it takes to make a star? Well, I have to say that even now the details are not yet known. Astronomer is still trying to um, make the theory on star formation better, but how a star is triggered to form in a nebula, we still don't know. We propose two theory here. One is spontaneous, that somehow suddenly gravity pulls the materials in the nebula, and that makes the star form. Another one is because of the effect of another event happening near the nebula. So for example, if there is a density wave or a collision or a supernova, that helps the materials on the nebula to be pushed together, and therefore the hydrogen gas can form into a star. This, we don't know yet which one. So when a star is formed in a nebula, usually this is quite a well-known model. It starts from a cloud here with because one reason or another it start to be clumpy, and then when the hydrogen gas get together more massive, and it's actually experience a gravitational collapse, and the process continue, and finally it creates a protostar, so a ball of hydrogen gas here. It is actually not yet a star as we know they are. Is actually looking like this. So it will be spinning with a disk, because the process has to go like when we want to make a round materials, we put it in, we round it up. So this is what happened also in the clouds. So we have here the future stars with the materials from the nebula still, the protoplanetary disk, and these new stars, it has lots of energy. So the energy has to come out somewhere. So usually from the two poles. So this is the bipolar flow here on what we call T Tauri star. I will tell you more about it on the next slide. And when the star, the pre-star, shed all of these extra materials, we will see the central stars, the part which will become a star, accompanied by the excess of the disk here, which probably usually become planets as in our solar system. So this is in brief the process of making a star. And in reality, how do they look like? So this is the data that we collect on protostars or pre-stars here. We call it also droplets because of the shape. So you see here, it's surrounded by the material. So this actually, the dots that you see here, the bright dots is the protostars, the part that will become stars with the disk. And this is the jets. That is, so this is zoom in on a certain part on the Orion Nebula. We will see it later. So, but most of the time what we see is only this kind of stars, this kind of object. So we collect a lot of data of this type of objects, and we try to compare it with our models. And now I will show you a zoom in through the Orion Nebula, where we found many of these protostars. So this is an illustration. We don't actually get a data like this. So but when we combine all of the data, we can see this. So as we zoom in, we see some of these little droplets there. And if we can shed the outer part, the gas part, we will finally see the protostar here at the center with the jets and the disk there. So this is what we see. And if we can get closer to that kind of object, this is an example here. The star, the protostar at the center is hidden by the disk. You remember when there is gas, we cannot see behind it. But here we can see the jets from the two poles there. So this confirms that this is a young star still hidden by its disk, but it's already giving this jets. So this kind of object, we call them as a T-Tauri stars. This is protostars or young stellar objects there. So when the young star or protostar expelling all these jets continuously, and finally when the materials finish, it's not infinite. So at some point the materials is gone, only then it becomes visible, and we see it as a T-Tauri stars here. It's a very active kind of stars. Some of the astronomers are specialized in this kind of stars, T-Tauri stars, so they have to study hydrogen nebula, star formation, star forming regions, young stellar objects, which not my field, but some of the astronomers are working on this. And now let's go back to Hertzsprung-Russell diagram. How this process will look like if we put them on the Hertzsprung-Russell diagram. And actually, yes, we can. So here, I start from this plot on the right. This would be the nebula here on the most right part on the screen. And due to gravity or external effect process, the nebula start to collapse. And it's actually a form, you see here, the radius is getting larger to the top right corner and getting smaller to the top left corner. So when a star is formed, because the gravity pulls the materials, the object, the protostar, start to be more and more compact, and actually it's going down to the left here. And if we see an example of our sun, it will follow this kind of track for one solar mass, and it will end up on this location on the Hertzsprung-Russell diagram. And different kind of mass, the different kind of protostar with different kind of mass will follow a different part, a different track on the Hertzsprung-Russell diagram. So if we have more massive star here, it will go on a higher part on the Hertzsprung-Russell diagram. So how long does it take? Here, you can see how long does it take to make a star. And apparently to make more massive star, it's faster than to make smaller stars, because the gravity works better, easier on more mass. So here to make 100 solar mass star, it will take 10,000 years. And to make our sun, it takes 1 million years, while on to make a star, which is 1/10 of our sun mass, it will take 100 million years. So it takes a long time just to make a star. So this is a point to take home. Stars of different mass will follow a different track on a Hertzsprung-Russell diagram, and stars of different masses will appear on a different location, different points on the Hertzsprung-Russell diagram. And this will tell them how to evolve. And before going there, not all the stars which made in the nebula will become stars. Some of them are actually failed. This is what we call brown dwarfs. So a star which form in the nebula cannot be too small or too big. So you see the guideline for the mass here, it cannot be less than this or more than that. Although we do find a few which is slightly bigger than this. So this is what we call the mass cutoff of the main sequence star. So it cannot be lower than certain mass or cannot be bigger than certain mass there. All right. Uh, so for this kind of star, brown dwarfs, they don't do nuclear fusion. They're actually shine because of deuterium burning, because they are sent the temperature inside the star, they're not high enough to be able to do hydrogen nuclear fusion. So the limit to do deuterium burning is about this mass there. So you see here the comparison of our sun, a red dwarf stars. So you see the temperature also here. And as we go more smaller and smaller stars, we call it L dwarf, T dwarf. This is just a name. So you see here the temperatures. And finally, this between white dwarf and Jupiter, these are not stars anymore. So these still stars, but these are between stars and brown dwarfs. So what is the smallest stars known to this day? It's this one, this guy here, 2 mass 05. This is the location, right ascension and declination. So 2 mass J0523 and the declination is minus 1403, this star. So it's a star which is smaller than Jupiter actually.
Co-host?
Sir, nawala po
Nawala,
siya.
akala ko ako yung wala. Ako yung nawala ng internet. Kasi nag-post. Nawala siya. Ay,
Si
sige.
ma'am.
Paantay lang po natin na makabalik po si Dr. Puji Irawati.
Opo.
Akala ko ako yung walang net kasi naka-post. Siya pala. Okay. Guys, pantay lang tayo ha. Wait lang natin si Dr. Puji. Salamat. While waiting for Dr. Puji, maybe may announcement si Gian.
So, yun, good morning everyone. Meron po tayong AstroChats mamaya, yung second half ng AstroChats around 2 p.m. po. Same link given to you. Our resource person for later is Dr. Ernest Makalalad of Department of Physics, Mapua University. Yan na po. Thank you.
While waiting po for Dr. Fuji, so maybe water break muna or bathroom break para po sa iba. Salamat. Guys, Dr. Puji sent a message that she is having a connection problem, so we will just wait for her to join again our group. Thank you. Dr.
Hello?
Puji, hi.
Yes. Yes, I'm really
Welcome
sorry.
back.
Yes, I'm terribly sorry for the interruption. I will try to share my screen now and continue from where we got interrupted.
Yes, please. Thank you.
Okay, so share screen. Hmm. Um, cannot find my screen. Wait a moment. Excuse me. Okay. So maybe where were we? The right. Um, so share screen. Hmm? How do I do that? Oh my goodness. All right.
So guys, so while waiting for Dr. Puji, so if you have questions or inquiries regarding our topic for today, so please write them in our chat box. So for the interest of time, we will just read them in your behalf. So we would be glad to raise them to our speaker. Thank you.
Seems like, how do I do that? Seems like I can share the screen here. That is, okay. What's going on? Mhm. All right, is it okay now?
Yes.
Yes.
All right. I'm really sorry, everyone, for the technical problem. I will try to continue where we left off. So the smallest known star, what we know is this guy here. You can look it up more. It was found in 2014, 6 years ago. There are also a list of historical known of list of smaller stars, but at the moment, since the past 6 years, this is it. So it's an L dwarf stars with a very faint magnitude, 21 magnitude here. The temperature is very low and it's actually, in terms of size, is smaller than Jupiter. And what about the most massive stars? Um, what we know is this one, R136A1 is a Wolf-Rayet star with a mass of 265 solar mass. Although the astronomer predict that it was formed as a 320 solar mass stars, but it has since lost some of its mass. And from when we observe it, so this one, it's in the Large Magellanic Cloud in the Tarantulan Nebula. So if we zoom in, this is the Tarantulan Nebula here. We zoom into the heart of Tarantulan Nebula and going in even more. And on this region here, so this is 4 by 4 arc second. So this is the guy there, R136A1. So there are a few massive stars on that location. So this is the known star, which is the most massive at the moment, although it's not in our galaxy, in the Large Magellanic Cloud. So this is our star, Sun, and this is the R136. All right, now we know what kind of star was formed in the nebula and how do they evolve from their location on the Hertzsprung-Russell diagram. We need to start with what we call actually a main sequence stars. A star is called as a main sequence stars if it's having a hydrostatic equilibrium, so meaning the gravity which pulls the materials inside and the energy from the nuclear fusion inside the center of the stars, they are equal. So they are balanced. So this is what we call the hydrostatic equilibrium. The energy of a star, it mostly comes from a nuclear fusion reaction. And for our sun and many other stars, they usually stay on the main sequence for as long as 90% of its life until the hydrogen runs out. So this is theoretical calculation of the lifetime of a star based on their masses. So our sun, it's based on its hydrogen content because it can shine because it's doing nuclear fusion, burning, transforming hydrogens into helium. So this, our sun, it predicted to live for about 9 billion years, and it's actually already about half now. It still has, it still have the about half to go to, so 4 or 5 billion more years. But stars which are more massive than our sun, they live much, much longer. So you see here, 50 solar mass star will live only 500,000 years, while a small star, less than our sun, it will live very, very long on the main sequence. So this is a simple calculation how we know based on the mass of the star, how long will it stay on the main sequence. So transforming hydrogen into helium, how do we know that stars are made of hydrogen and helium? Somebody else did all the hard work, which actually 100 years ago almost, is a lady, Cecilia Payne Gaposchkin. She was the first woman to obtain a PhD from Harvard College in the United States. She worked on, it was already collected 4 decades of data. So it's 9 volumes of stellar spectra. Each volume contains 250 pages. So you see data, data, data. This is what we do. We collect all the possible data we can, make a theory and compare it. So she found that working on this data of stellar spectra, she found that most of the stars, and probably in the universe, that the most abundant material is hydrogen and helium. And at that time, 100 years ago, her finding was said as impossible because it contradicts the common concept that was accepted at that time, that sun and all other stars will compose with a material very much similar to Earth. So her finding was very contradictory, and most of the scientists at that time, they didn't like it. But it's actually correct. So she was having a really difficult time, not only as the first female astronomer, and also publishing a breakthrough finding. So this, you remember Russell, the person who made the Hertzsprung-Russell diagram. So this person declared that her finding was impossible, but the same person actually proved that her result actually correct. So this is the abundance of the elements in the sun. So 92% by atoms, hydrogens and then helium, but by percentage of mass, it would be 73% hydrogen and 25% helium, and the rest is heavier elements than hydrogen and helium. So she found that stars are made of hydrogen and helium, and that's paved our way to the current stellar evolution and stellar nucleosynthesis. So thanks to her and all the hard work during the past 100 years, we know that sun and other stars, they can shine because of what we call a nuclear reaction, transforming hydrogen into helium here, which needs a very hot temperature. So at the moment, it can only happen in the core of stars. We cannot produce it on Earth. So this is what's going on in the sun, inside the sun. So this energy comes through, and after it gets out of the atmosphere, the photosphere of the sun, it will reach the Earth, and that light is the data that we are taking for the astronomer. And for a hotter star, actually more massive stars, hence the temperature inside is hotter, they can transform helium into heavier element, in this case carbon. For our sun, not yet. I will tell you in very soon why not yet. So for this kind of star, inside the core, they will transform or doing helium fusion, or what we call the triple alpha reaction. So as you see here, it needs even higher temperature, so 100 million Kelvin. For stars which are more massive than that, they can do even more. So based on the temperature, they can do first hydrogen burning, hydrogen to helium, and then helium to carbon, and then to oxygen, and then to silicon. And the final product is iron, and you cannot transform iron into anything else. Inside a star, it actually disintegrates when you reach iron here. So this is the structure of massive stars. You see the hydrogen at the outer layer, and coming inside, it's heavier and heavier elements. And you see here the time scale of burning each element into heavier version. All right, so I will try to go to keep the time and go a bit more quickly here. Post-main sequence evolution. So what happened when the stars runs out of hydrogen inside the core? So it you see again, Hertzsprung-Russell diagram is a very important diagram in stellar evolution. Each star with different mass will follow a different track, and they do different things along their lives. For our sun is here still on the main sequence at the moment. When it runs out of hydrogen in the core, because it's limited, it is what it is, what the sun has inside the core. So when it runs out of hydrogen, it will come out of balance, because it cannot produce energy from burning the hydrogen into helium. So it will move from the main sequence here, actually become larger, become a red giant here. So when the hydrogen runs out in the core, the sun, inside the core, the sun cannot produce energy. So that's why the sun is out of balance, and it's getting out here, getting bigger. And when the core reach a higher temperature, when it finally can transform helium into carbon in the core, so here is the point. Finally, the sun has a little bit more energy. It can do it now by transforming helium into carbon. And then when that also runs out of helium, it's going out of balance again. So when it happens, the sun getting larger and larger and larger in radius. So as you see here, this is the sun now, and as a red giant, this will be the sun later. So when we don't want to be here on Earth when the sun evolves into a red giant, because it will engulf its planets. So this is what's inside the stars during each of this process. Now what happens after that? So when it becomes red giants, and our sun, unfortunately, is a small star, so it cannot reach in the core temperature more than 100 Kelvin, so it cannot transform carbon into heavier elements. So that is the end for our sun. And after that, after it reaches the red giant phase, it will actually expand and expand and expand the envelope into what we call as a planetary nebula here. So it will move quickly from this point all the way to here. This is actually, it doesn't move, it's just the envelope or the outer part of the sun expand very quickly, rapidly, and it's getting thinner and thinner and thinner, and it's actually bare the core, which is a white dwarf star at the core. So here an example, as you see, this is remnants of a sun-like stars evolution. So with the mass is about this size. The image, the size is to scale. So the planetary nebula has different sizes as well. And in some of them, you can actually see the central star. Here, for example, is a very nice bright white dwarf there, or here, in some of them, we cannot see it. So these are the end point of sun evolution. So this, the white dwarf at the core will be of similar size to Earth, with the size of about 1 solar mass or less. And we already knew what's inside the white dwarf. It's a crystal core. And what about larger stars, more massive stars? They have different story. So in brief, stars which are much larger than our sun, they will become, they will experience a supernova explosion. It will become a star larger than a red giant of our sun. It will experience a more violent explosion called supernova, and they will become neutron star or black hole, depending on their mass. And you know what's inside of these stars here. So massive star evolution, supernova, what actually a supernova explosion? So when this happened, the explosion is so violent that it destroyed the whole stars, leaving, sometimes it has the neutron stars inside. So this is a well-known example, a Crab Nebula. It exploded in our galaxy 1,000 years ago, which was recorded by a Chinese astronomer. So it was really bright that you can see it during daylight. And further on, some 100 years later, another astronomer noticed that it's actually expanding. It's getting bigger and bigger. And now, thanks to modern technique, space telescope, X-ray telescope, we knew that in the heart of the Crab Nebula, we have a young pulsar. So it's a neutron star which starts spinning. So this is an example. So how many more? We actually have quite a few in our galaxy. So these are supernova candidates which possibly exploded in the past in our galaxy. You can check here the years. You can also visit the link to check more details. This is the Crab Nebula that I mentioned, and a few more. So these are what we see now. So we are trying to prove that this was actually used to be a very massive star which exploded. So the most recent supernova in modern days, the closest one, was actually supernova 1987A. Unfortunately, I was too young at that time to notice this very big event happening. But if you ask a more senior astronomer, they can tell you more story about this. So this was it was on the Large Magellanic Cloud again. So that's why we can observe it really clearly without the dust which exists in our galaxy, which blocked our view. So this was before the supernova here, and this is during the supernova. So it became much brighter. So that's why it called it a new star. And so this is what possibly the story of supernova 1987A. So it was formed, the star, 11 million BC. So not too long ago. So you can see that it's quite massive star, and it lives only about 11 million years. And you can follow, you can check the image later. So it, as usual, runs out of hydrogen, helium, and so on, and it becomes a red giant. And when it comes to the iron, finally it cannot do more than that, and finally it exploded as a supernova on 24th February 1987. And so what actually happened during a supernova? So let me play this. So this is an illustration of an actually supernova type 1a. I will tell you more about that later. So this is a quick movie. So it's suddenly this burst of explosion and energy. We observe it in so many different wavelengths. And after that, all the materials comes expanding from the center. So this is an illustration for Tycho Brahe, observed by Tycho Brahe in 1572. So this is the remnants that we see nowadays. All right, so how do we know the patterns of this supernova? Basically, we take the spectra and we take the lights, or the light curves, the photometry here. From their spectrum, we will know what type of supernova they are. So type 1a or type 1c, 1b, type 2. And they're actually formed by different kind of objects. So this is an investigative tool by astronomer. When we know this, we will know what the object causing it. So there is type 1a, it has a different light curves than supernova type 1-2. And it's actually type 1a is created usually by a binary star, so a white dwarf getting extra materials from the companion, and it's exploded because it cannot take more materials. And type outside type 1a is actually the core collapse supernova. So this is a thermonuclear supernova. This is core collapse supernova. So I'll come to the point why stellar evolution is important for every astronomer. It's a key to understand every single object in our galaxy and in the universe. And if we know the story of one object, we can look back in the past, or we can even predict the future of that object. And stars are the smallest building block of the galaxy. So if we know how the stars or the population in that galaxy, we can also guess how that galaxy will evolve and will change later. So we can go into galaxy evolution in the future. I just would like to say briefly that we talk about single star evolution. Binary star evolution is another story because it is more complicated when you put two stars together, because the stars are confined on what we call the rho slope, which basically, you know that every mass in the universe will bend space-time. So when we put two stars together, it's actually making this kind of a unique shape, or like a balloon or a teardrop. And the stars, this is the area that a star can expand, but no more than that in a binary. So when we have a binary star, their evolution is much more complicated. This is a very famous example, an Algol binary. The astronomer observed that there is brighter, bluish, whitish stars, but actually smaller than the other one. So what's going on here? We know that brighter star, bluish stars should be more massive than red stars, but not in this case. So apparently, tracing back, finding more data, we found out that actually the red one used to be more massive. It evolved first, giving some of its mass to the companion here, and it transformed the companion into a more massive star, while this one has became a red evolved stars. Another very unique example is what we call high mass X-ray binary. It has, as you see on the screen, complicated evolution. We have a black hole, sometimes also a neutron star, accompanied by bright blue stars here. So how we make this kind of system? It's apparently through this complicated process. And nowadays, we have many more different kind of binary, exotic binaries. And for each of them, astronomer have to find out, has to investigate how they were formed back then. How come we have this combination nowadays? So binary evolution pose even more challenges for astronomer, and especially in the field of stellar evolution. Um, as a closing remark, despite all the challenges in astronomy in the world, I would like to emphasize again that astronomy is an advantage, not a limitation. Why? Because as an astronomer, we can deal with billions, data of billions of stars and galaxies. We have to deal with multi-wavelength data, multi-messengers from all different kind of telescopes, and often we have to do real-time data as soon as we get it, because when we have a supernova exploded or a gravitational wave, we cannot wait. Somebody else has to observe. So we have to alert our colleague as soon as possible so we don't miss this event. So we can deal with this huge amount of data in a very short time. And apparently we can apply it to COVID-19 data. So this is an example. A professor, a colleague from Australia, Professor Matthew Bales, he usually work on gravitational waves using supercomputer, uh, and he's asked to work on COVID-19 data because he has the method, the capability, and he has the means, the supercomputer ready with everything ready. So basically just put the COVID-19 data there, we get the result, and it can actually predict the possible outbreaks of COVID-19 in Australia even before um, the official knows that there is an outbreak there. So this is one of the use of astronomy nowadays. So it's actually astronomers can do so many things here. And with that, I will stop. Thank you very much.
Thank you, Dr. Kuji, for your very informative presentation. Despite your connection problem, you still give an effort to proceed and give us that knowledgeable presentation of yours. I'm sure that everyone has been static learning more about stellar evolution. To share and review these realizations, we have student correspondents from Department of Earth and Space Sciences. May we call on Mr. Mark Edsel Danau for your takeaways.
Thank you, Sir Gian Santos, for introducing. And first of all, Ma'am Puji, I would like to thank you for your act of willingness to give us this wonderful presentation. And in addition, I also want to become an astrophysicist like you, Ma'am. And I'm so happy to learn from an expert of my favorite field. Uh, and on behalf of BS Astronomy Freshmen, we learned a lot of things in this presentation. And also, this is a very timely topic because our next discussion in our introduction to astronomy course subject is about stellar evolution. And that would be huge, and this presentation would be a huge head start to us. And as a freshman that will enter the deeper part of astronomy, I learned some terms that I only found out today or having a little familiar with, like head-sprung Russell diagram, and on how that diagram is so important to astronomers and for the stellar evolution, and also the gene criteria, and on how the cloud should be right to become a star, the three T Tauri stars and type of supernovas, and also my favorite astrophysics term, the rock globe. And I learned and I surprised that there are stars that is smaller than Jupiter, and having an insight to the most beautiful astronomy thesis ever made by Kapotchkin. And all of this is, I am so curious and I am craving to learn all of this to a great extent. Uh, and I was fascinated to this in this presentation and how the star changed with time, how it depends on its mass, luminosity, how it starts as a nebula to protostar, or how it grows to becoming a great main sequence, to a giant or a supergiant, to a planetary nebula again, or a supernova, or how it die to become a white dwarf, a neutron star, or a black hole. Although that is some theory, but most people don't realize it. That stars have lives. They get born, they live their useful lives, and when they run out of fuel, they die. It's sad that we can't see it in our time scale or in our lifetime or in our limit human life span, or but I would be glad also because that would be extremely bad for us. And thanks to our instruments like telescope and using space objects like Gaia and using some space scientific methods, we could be back on time to see how star like our sun will progress. uh, Also, it is beneficial to us freshmen to learn all of this because studying all of this, we can understand where we came from, when we are going, and how the law of physics works in these conditions that is under conditions that is not possible or almost possible to recreate on our planet Earth. It can be recreated, but in a short scale and in a short scale of time. And so far as I am aware, the purpose of astronomy is to understand the world that we inhabit. And as we know, as we are driven to explore the unknown, humans are known that we are always curious for discovering new worlds. We are pushing the boundaries of our scientific and technical limits, and then for the pushing further for our future. And being a part of the universe that can understand and enjoy itself is what makes me the most alive and the most happiest human on earth. And I agree with Neil deGrasse Tyson that when I study the universe, it doesn't make me feel significant. It makes me feel huge. And for me, the biggest achievement of a human being is to discover the true nature of the cosmos and our place within its order. And for lastly, I truly agree with the saying that change is constant. And thank you very much for that.
Thank you, Mr. Denau. We move with another correspondent, Mr. Jorn Jasper Raquel.
Good afternoon, ma'am. So thank you very much for that wonderful talk. And one of the major takeaways from your talk is especially analyzing data, the struggle of most of the junior college students here in the Philippines. So struggling with the data analysis, especially. And I have learned that in studying stellar structure, we can use two simple steps. The first is to construct models, and secondly, compare these models with the observed properties uh, during our observations. And as we all know, there are six parameters that help determine the evolution of a star. And what piques my interest the most is the existence of the star forming regions and how is the energy density all throughout these regions help to form new stars and develop into a new exciting field of astronomy. And lastly, uh, what we usually do in some of our researches is we use these photometric and spectral data to analyze and extrapolate information from these celestial objects. And that would be all.
Thank you, Mr. Jorn Raquel. Now we move for our last student corresponder, Miss Bea Kaindig.
Good day to all. First and foremost, thank you, Dr. Puji, for that inspiring and very informational talk, and to the Narit and CARD collaboration for making this event possible. As students and aspiring astronomers and astrophysicists, stellar evolution is one of the most essential topics that we must study. This subject is very engaging as it invites us to study the origin of life of stars and to prove that they are more than just twinkling objects in the night sky. Rather, they are interesting laboratories full of information waiting to be discovered. Thank you and clear skies to all.
Thank you, Ms. Kaindig. Now we proceed with the open forum. Let's hear it from our audience in the Zoom room from Miss Margaret Custodio.
Good morning. Thank you, Gian. So, our first question for Dr. Fuji is from John Peter Juarez. So, why, when we look at the sky, we can only see the and blue and white star only? Thank you. That's the first
Oh,
question. Yeah.
uh, yes. So in theory, we supposed to be able to see the color of the star as the color of the rainbow. So you see that from purplish to reddish. Um, each color will tell you the temperature, the effective temperature, which comes from the outer part of the stars. Unfortunately, our eyes, as a human, our eyes are not very sensitive to this kind of coloring on the stars. So what we see mostly is blue, white, yellow, red. So we cannot see green. Apparently, it's there, but we don't see it. So it's so on the visual data, optical data, what we see are only this kind of color, which are limited by the capability of our eyes to see this color. So when you see actually this beautiful different kind of colors, green, purples, and that kind of thing, that's is a combined wavelength, different kind of data to highlight different kind of properties of the stars. For example, if animals on Earth which has a different kind of eyes, I think lizard, they will see stars in a different kind of color. So this color, blue and white, we don't have purple. Unfortunately, that's because our limitation as human. I hope that answered the question.
Thank you, ma'am. So, the second question is from RB De Castro. Good morning. Is there anything that significantly differ Hertzsprung Russell diagram to the Morgan Cannon system, or is any difference at all? He noticed that they use both the sequence of stars from Morgan Cannon system.
Uh, yes. So the what you see on the Hertzsprung-Russell diagram, I'm not sure if I can share it, but yeah, it's combined actually. The Morgan-Cannon system has the spectral type, so O, B, A, F, G, K, and M, depending on their temperature, while the Hertzsprung-Russell diagram, they just put whatever temperature there on the x-axis with their brightness and luminosity. And so they are different, but what we use now is actually a combined version of both. So on Hertzsprung-Russell diagram, you can also put the Morgan-Cannon system, the OPA, FGKM, the spectral type, because they also signify the temperature of the stars. So they are a different system, but in the purpose for stellar evolution, we combine them. And also there is the the spectral type on the type of the stars, like V for main sequence stars, one for supergiants. It's usually when we signify um, a star, we will know, okay, what is the spectral type? So for Sun is G2V type stars. So with this, we can also put the stars on a Hertzsprung-Russell diagram, and we know the luminosity, the exact temperature, and how the star will evolve and how the star was formed before. So it's a combination of both.
Thank you. The third question is from Kairi Dawayan. Is it is it the end of the human race, including all organisms, when the sun evolved into a red giant or supergiant? And finally, if it will explode, what will happen to us? Possible extinction, maybe?
All right, yes. That is an interesting question. It will be the end for Earth for sure. As a human race, possibly we would be able to do space travel by then. I'm not sure. This would be for your generation to answer. But I have to mention that you remember from the talk that before the sun even expand larger, it will experience that the hydrogen inside the core is finished, meaning it cannot produce energy. So it doesn't shine as it used to be. And what we cannot answer is what happened to Earth and other planets and all the inhabitants of Earth when our sun is not shining anymore, because sunlight is a very important aspect of our life. So we have to answer that first. So that probably happened before the sun expand into a red giant and engulf its planets.
For the fourth question from Ken Matthew Barcelona, if by chance the Jupiter actually become a star, how much is a difference will be in our solar system?
Right. Yeah, I kind of remember that there was a theory that possibly Jupiter is supposed to be the binary companion of our sun, but it failed. I am not an expert in this field, but if Jupiter happened to be a star, it would be, as you see, from the data or theoretical point of view, based on its mass, it cannot be a star. But if it could, the lights probably it would be a red uh, star, very tiny, with very low energy. I will have to see first how much energy it produces, but probably it's not much. Probably we can see it, but we will not see its effect on other planets because of the distance is quite far. But again, this is um, a guess in my mind. We will have to see what matters is the energy that comes from a particular stars. And if we talk about how it affects humans, then we have to see how much energy we receive on Earth.
For We will only have two last questions here on Zoom chat. Then we will proceed for the Facebook questions. So for the last two questions, we have from Bia Marika Hendy. Good day. I have read a research article questioning Proxima Centauri's status as Alpha Centauri. If ever it is proven that the composition of the proxen varies greatly from the Alpha Centauri AB, will the status of it as the third companion of the system be questionable? Thank you.
Right. Yes. Alpha Centauri and Proxima Centauri. I stopped at the binary system. I didn't even touch the topic of triple system. Uh, So the Alpha Centauri, or Proxima Centauri, being the closest star to our sun, is indeed a very interesting object, and we even consider a possibility to go there. Um, I think, the triple system, the Alpha Centauri uh, A and B, they are a very well-known spectral type, and you know from the image they are bluish star. Um, while for the okay, the binary system there, they are well known, they are well established, and what we are interested in. So it to consider whether it will change our perception when the data, probably not. We are still considering, of course, the possibility of going there or to move there, or but that would be for the exoplanet field to answer. Um, the star itself, the system itself, it's quite well known. What we are doing now in astronomy is to gather more data, high resolution, better data on each of the system, of each of the stars in the binary. And so if in case we human decided to visit this system, whether the astronomy contribution would be to give an information whether it is worthy or not worthy. Um, I would say that one. So it will not change much, except that whether what we will know later about this system as a worthy neighbor star to visit or not. I hope that answer the question.
And for our last question, actually, he has a four question. So first is the what distinguishes a protostar slash Proli D T
Progress, yes.
Tauri star from a pulsar? Then the other question is where can place magnetars in the HR diagram? Do the energy density of star forming regions remain constant through time? And are there ways to predict how many stars will be formed at a star forming region? Thank you.
Okay, magnetars. So as you see in the Hertzsprung-Russell diagram, the axis is the temperature, the x-axis, and the y-axis is the brightness. So an object has to have a brightness, so light, visible light, to be put on the Hertzsprung-Russell diagram. So as you see, we don't have neutron star there. We don't have black holes. And magnetars here, it's a neutron star kind of object, meaning we don't see it in the visible light. Only a neutron star, we will see it when it interacts with another object. For example, if there is a companion nearby, then we see the effect of that on the neutron star, but not the neutron star itself, or magnetars in this case. So magnetar is a very hot topic nowadays in astronomy. Last I heard that we are having one magnetars which produce a fast radio burst in our own Milky Way galaxy. Um, so unfortunately, no. If an object doesn't have a light, we cannot put it on the Hertzsprung-Russell diagram. And excuse me, can you remind me of the last question?
The last question is wait, are there do the energy density of star forming regions remain constant through time? And are there ways to predict how many stars will be formed at a star forming region?
Right. Yes. Thank you very much. So the density wave, it's really a big question that we cannot answer at the moment. Possibly they they are different from time to time and from place to place, from location to location on the star forming region. We don't know yet where, when this density wave will occur. We are the astronomers working on the star forming regions are working so hard to do that, and but how many stars can form in a nebula, it depends on the size of the nebula. If we know that the nebula has the right mass, within certain masses to form a stars, so smaller nebula will form smaller kind of stars. So for example, the Pleiades cluster here, it probably comes from a smaller kind of nebula, while the Orion Nebula can produce thousands, hundreds of thousands of stars because it's so large. So it will depend on the mass of the hydrogen inside the nebula.
So that will be all for our Zoom. Thank you, Dr. Puji Irawati. Now we proceed with the queries of our audience from the Facebook Live. Let's hear it from Miss Princess Tusho.
Good morning, Dr. Puji. So we also have questions in our Facebook Live. So the first question is from Thea Chelsea May Moya, an undergraduate student from astronomy. So she wants to know, why are blue stars unexpected in such clusters? And if stars that stick together mix their material thoroughly when they collide, how might you explain such blue stars?
All right. So blue kind of stars, from the stellar evolution theory, they are usually young objects. So they are recently formed, and therefore, most likely, they are usually always correlated to a nebula nearby. It's either the nebula hasn't shed completely all the leftover of the hydrogens, or it's still actively forming. Usually only the actively forming region of the nebula can form this new star. It has to have hydrogen, of course. So that's why usually blue stars, they are connected with a nebula one way or another. They just recently formed, just recently been born. There are cases like star clusters, so young star clusters, but they are, by young meaning a few million years ago was formed. So they are, but in this kind of star cluster, if you happen to search images in Google, they also usually still has lots of dust and bluish kind of appearance, because they are still very young and still actively forming the star there. And stellar merger or mass transfers, actually, yes, they are the kind of process that can help a star change in appearance. And so, for example, we have a stellar collision, one object that was proposed as a result of a star collision is a blue straggler. You can look it up. It was predicted as a result of a stellar collision, and because of this collision, the two stars, they merging together and forming a larger and bluer star, and which appears on the top part of the Hertzsprung-Russell diagram there. And or in the case of Algol, it can also one star transfer its mass to another, and the mass will be accepted by the companion, and as a result, the other star, the accretor, will increase its mass and becomes bluer. So there is process in astronomy, and yes, we know this for a fact. Although for the stellar merging, we are still gathering more data to confirm and to make sure that when we see a star, a blue star, we know that whether it's resulting from a merging of two stars or more, or whether it just formed from the nebula as the way it is. We are still working on that.
So thank you, Dr. Puji. And another question from our astronomy student. Good morning, Dr. Puji Irawati. I am Kay Lurer from CIT 33301A. Is it possible for white dwarfs to reignite or come back to life? If yes, how can it happen? Thank you.
Can you please repeat the question? I'm sorry.
She wants to ask, is it possible for white dwarfs to reignite or come back to life? If yes, how can it happen? Thank you.
Right, a white dwarf. A white dwarf is a special case. So a white dwarf star will, if it's alone, a single white dwarf, it will stay as it is, shining from whatever hydrogen which is left in that tiny stars. So it will shine, and it doesn't have a nuclear burning. So basically it's just from gravitational process and pressure there that it shines. Once this process is finished, it will become a black dwarf at a very, very long time in the future. So this is a theory that we made, although we haven't seen a single black dwarf in the universe, because we still have to wait a long time to see that. A white dwarf can get bigger, meaning it can get mass transferred by the companion, but a white dwarf cannot reach a mass larger than 1.4 solar mass. And we know this for a fact because of a supernova. When a white dwarf reach this limit, 1.4 solar mass, it, instead of getting bigger and bigger, it explodes, because the condition there, the pressure, the temperature, it cannot accept more mass than 1.4 solar mass. If it's more than that, it explodes instead as a supernova type 1a. So in terms of white dwarf collision, possibly a source of gravitational wave, we are still hunting for the outcome of this two white dwarf when it collides, what it will become. But it will produce some sort of a possibly explosion, and if yes, what would be the leftover of that? We are now in that time in astronomy to find out what is going on, the future of this kind of system. I hope that answered the question.
Thank you, Dr. Puji. So another question is from Jenny Lee Jaiko. I just want to ask if there are any chance that Radcliffe wave will make some difference in our own sun's behavior. Thank you.
Short answer, no, unless it happens very, very nearby, this gravitational wave collision. So gravitational wave, from the name, it actually creates ripples in time and space. So basically the time and space will oscillate because of this, the movement of two objects colliding. At the moment, the effect that we detect here on Earth is very, very tiny, that we have to create a super sensitive instrument, the LIGO and Virgo, to detect this kind of ripples on a gravitational wave. So for our sun and Earth, it will have no effect at all, unless, as I mentioned, there is a gravitational wave event happen nearby. But in that case, we, I think, would know way beforehand, because this gravitational wave would come from kind of massive kind of star. So either we feel the optical wavelength effect way before the gravitational wave comes. So, and I don't see that we have, I don't see yet that we have such object nearby in our solar system or in a nearby solar neighborhood.
So thank you, Dr. Fuji. So that will be our last question.
So thank you, Ma'am Princess. And thank you, Dr. Fuji, for your active response to the queries of our audience. Moving on, to award the certificate of recognition to our resource person, may we please have the Science Research Specialist of the Center for Astronomy Research and Development, Ms. Margaret Custodio.
Oh, wait lang po. Is my screen sharing already?
Yes.
Yes, ma'am.
Okay. So, good afternoon. To award this virtual certificate, may I read this? The Department of Science and Technology, together with Rizal Technological University and Center for Astronomy Research and Development, presents this certificate of appreciation to Dr. Puji Irawati for imparting invaluable passion of scientific knowledge and development during the Super November AstroCHATS Stellar Evolution, held on November 27, 2020, signed by ASOC Professor Ryan Manuel D. Guido, Program Officer of Center for Astronomy Research and Development. Once again, thank you, Dr. Puji Irwati.
You're welcome, and thank you very much for inviting me for this exciting event. I hope to see um, much better future for astronomy in Southeast Asia and especially in the Philippines in the future.
Thank you, Ma'am Marga, and thank you, Dr. Fujirawati. Before we depart, may I request everyone to open their camera so we can have our group picture.
Nag-ayos pa iba eh.
So ready na po. One, two, three. Second frame po. One, two, three. Third frame po. One, two, three. Last frame po. One, two, three. Yeah. So that will be all po. Thank you once again, Dr. Fuji, and to everyone who joined us to this morning session. Another reminder po that we will have the second half of today's AstroChat at 2 p.m. and I invite everyone to still participate with the same ano po, same link given to you po. That will be all. Thank you.
Thank you.
Thank you, everyone. See you again.
Thank you po.